Okay, in this video I'm going to be using the method of contour integration to evaluate the so-called Fresnel integrals, and these are the integrals from 0 to infinity of sine of x squared and cosine of x squared. And I'm going to use a contour and my function f of z to try and evaluate both of these integrals all in one go. So first of all, I'm going to define f of z to be e to the I z squared, and I'm going to use this contour. It's going to be an eighth of a circle. So if you take one circle and chop into 8 equal pieces, you get this. So how it's going to work is I'm going to start from the origin, and I'm going to go forwards to the point R, and this point R is greater than 0 on the real line, and then I'm going to go round an arc, which I'm calling big gamma, and then once I've reached this point in the complex plane, I'm then going to head all the way back to the origin. Now the angle that this sector is going to make with this arc, the angle that's subtended by the arc, is going to be pi over 4, or 45 degrees, because that's 1/8 of a full turn. An eighth of 2 pi is pi over 4. And I'm going to have three separate integrals that arise from this. Obviously, I'm going to have the whole contour, but then I'm going to have the integral from 0 to r, the integral over gamma, and then an integral going back. Now, because this line from this point here to this point here is going back, in other words, in the opposite direction from the line from 0 to r, then the integral is going to have a negative sign. So if you imagine I'm taking let me just draw this. If you imagine I'm taking an integral over this line, or if I were to take this line and I wanted to map that line to this line, then not only would I have to multiply every point on this line by e to the I pi over 4, because you'd have to multiply a point by e to the I theta to rotate it by an angle of theta in the complex plane anti-clockwise. But then I'd also have to think about what would happen to the direction of the ray. So once I've done that, sure, it would be pointing in this direction, but I need to multiply it by -1 to make sure that it's actually got the right orientation. So when I actually write down my integrals, I'm going to have to be very careful about that. So what integrals do I get from this as a result? Well, I'm going to have the integral of the whole contour, which I'm calling c, of f of z dz, and that's going to be equal to the following three integrals. That's going to be equal to the integral from 0 to r of f of z dz, plus the integral over gamma, that's the curved bit, gamma, f of z dz. And finally, I'm going to have a negative sign here and integrate over this straight line, which I'm calling L. And that's going to be f of z dz. Now, this might be a little bit interesting because I'm not going to be using the residue theorem, nor am I going to be using the estimation lemma, so I think it might be the first video in this series where I don't use either of those things. So let's see how this turns out. Well, first of all, if I look at the poles of my function, e to the I z squared, that doesn't have any poles, certainly not inside my contour. So as a result, Cauchy's theorem immediately tells me that the integral over this contour is just going to be 0. So I don't need to use the residue theorem here, this is just 0 by Cauchy's theorem. And I'll provide a link to that in the description box below. Now I want r to tend to infinity, so this integral here is probably going to tend to something useful. So why don't we have a look at this integral first? So I want to look at the integral, let's see, integral from 0 to r of f of z dz, and by my definition of f, that's going to be the integral from 0 to r of e to the I z squared dz. And that's going to be the integral from 0 to r of e to the I, So what is z? Well, if I think about this as a real valued integral and call this a real valued integral, and call this e to the I x squared dx, then it might be clearer what I want to do. Well, I know that e to the I y is of the form cos y plus I sine y, so this is just equal to the integral from 0 to r of, let's see, cos of x squared plus I sine of x squared dx. And then if I let r go to infinity, so if I let r go to infinity like this, then I'm going to get two integrals, the integral from 0 to infinity of cos x squared dx, plus I times the integral from 0 to infinity of sine x squared dx. So basically the real and imaginary parts of this integral are going to correspond to the Fresnel integrals that I want to find. Okay, so that deals with this integral. So I've dealt with this one, and I've now sorted out this integral to an extent. Now let's look at some of these integrals. First I'm going to look at the integral over the curve gamma and see what I can do about that. So I've got the integral over the curve gamma of f of z dz. And basically what I want to do as usual is try and show that the contribution of this integral is going to be 0 to the overall sum. So how am I going to do that? Well, I've got the integral over gamma of f of z, which is by definition e to the I z squared dz, and I'm going to use a parameterization, or I'm going to use a substitution here. So I need to think about what sort of substitution I could make. Well, this traces out part of a circle which is going to have equation r e to the it, and t is going to vary from t equals 0 to t equals pi over 4. So at this point on the real line it's going to have t equals 0, and when I rotate all the way around r e to the it, at t equals pi over 4 I'm going to reach this point here. So let me write that down. So I'm going to make the substitution z equals r e to the it, and I want t to vary between 0 and pi over 4. So it traces out the relevant segment. And if I differentiate z with respect to t, I'm going to get dz by dt. That's going to be equal to ir e to the it dt. And if I just plug this back into my integrand, see what the effects of the substitution are, that's going to be equal to what? Well, the lower limit is just going to be t equals 0, and the upper limit is going to be pi over 4, so that means I'm integrating over this whole curve gamma. And what's e to the iz squared going to become? That's going to be e to the I, or the square of this term is going to be r squared e to the I2t, let's write it like that, and dz is going to be ir e to the it, so that's ir e to the it. And by the way, I'm going to want to try and show that this is going to 0, so it might be helpful to try and estimate this. I'm going to put absolute value signs here, just like that. And you'll see why I'm doing that in a second. So this is going to be dt. Okay, so now what can I do? Oops. Well, first of all, I can pull out the I, because that's just a constant, and that's going to give me what? Well, that's going to give me the absolute value of I times the integral from 0 to pi over 4 of e to the I r squared. Well, e to the I 2t, I know that e to the I x is cos x plus I sin x, so here I can just replace e to the I 2t with cos 2t plus I sin 2t, that's just by Duhamel's theorem, and I'm going to have r e to the it dt here. Okay, and now I'm going to, well, first of all I can get rid of this I, because I has modulus 1, and when I take the modulus inside, that's just going to be going to 1, so I can ignore this, and I'm going to have the absolute value of the integral from, I think this should say pi over 4, the integral from 0 to pi over 4 of e to the I r squared cosine 2t times e to the power I r squared I sine 2t. Well, I'm going to have I times I, which is I squared, like that, and then I'm going to have r squared sine 2t, and then r e to the it dt. And what is that going to give me? Well, that's just going to give me the integral, the absolute value of the integral from 0 to pi over 4 of e to the I r squared cosine 2t. I squared is minus 1, so that's going to give me e to the minus r squared sine 2t. And then I'm going to have r e to the it dt right here. Okay, so now what I'm going to do is I want to use the triangle inequality for integrals, which basically says that I can bring these absolute value signs inside. So I'm going to get the integral, well, this is not equal to, but less than or equal to, the integral from 0 to pi over 4. Let's see, I'm going to have the absolute value, or the modulus of I, e to the I r squared cos 2t, times the absolute value of e to the minus r squared sine 2t, times the absolute value of r e to the it dt. Now I want to have a look at each of these three terms individually before I do anything else. Well, first of all, I know that r is a real number, it's greater than 0, so r squared is a positive real number. T is a real number, so cos 2t is a real number. So that means that this whole thing is equal to 1, and you might ask why. Well, the modulus of e to the I theta is always equal to 1 as long as theta is a real number. So that's true for all real values of theta. If theta were a complex number, that wouldn't actually be true. So that's just equal to 1, so with the modulus signs I can get rid of this. Now for this term I can actually drop the modulus signs for pretty much the same reason as this one. I know that r is a positive number, so r squared is also positive. Likewise, t is a real number, so sine 2t must also be a real number. So I've got e to the power of a real number, and e to the power of a real number is always positive because the exponential function is always positive. It never touches nor goes below the x-axis. So this I can just say is greater than 0. So I can drop the absolute value signs and I can integrate this perhaps directly after doing some estimations. And for the same reason as the first term here, r e to the it, that's just going to be equal to r when I take the absolute value of this, because e to the it is value 1 for all real values of t. So that's going to give me, well, that's going to be equal to the integral from 0 to pi over 4 of 1 times this thing, which is e to the minus r squared sine 2t times r. So I'm going to have r there, dt. That r was quite small. Let me write it a bit bigger. R dt. Okay, and recall that in one of my previous videos, I think it's called an inequality for sine t, I proved this inequality, which says that the sine of t is greater than or equal to 2t over pi, and the way I proved that was using the mean value theorem. And I showed that that was true for all values of t belonging to the closed interval from 0 to pi over 2. But in the power of the exponential function, I've got sine 2t, not sine t, but I can very easily remedy that. And if I look at the inequality for sine 2t, well, if I just replace t with 2t, I'm going to get 2 times 2t, which is 4t. That's 4t, not 40, divided by pi. And my inequality holds for t belonging in the interval from 0 to pi over 2. So in other words, 2t, it holds for 2t belonging to the closed interval from 0 to pi over 2, but that's basically the same thing, or equivalent to saying that t belongs to the closed interval from 0 to pi over 4. So if I look at my region of integration, it's from 0 to pi over 4, so my inequality is valid and I can use it at any point in this interval. Okay, so if I just draw a box around this, just so I don't confuse the two parts, I now know that this is going to be what? Well, this is going to be less than or equal to the integral from 0 to pi over 4 of r e to the minus r squared, and here I'm going to have 4t over pi. So 4, let's write here, times t dt. Well, this is something I can integrate directly. I think it's probably best if I move all the way down here. And this is something I can integrate directly because it's of the form e to the power of some number times t, and minus r squared 4 over pi is certainly a real number. So how am I going to do that? Well, I'm going to get the following. I'm going to get what? So I'm going to have to do 1 over this constant here, and that's going to be minus pi over 4r squared times r. So that's going to be minus pi over 4r squared, and I'm going to have the factor of r from the integral, from the integrand, and I'm going to have to evaluate e to the minus what was it, r squared 4 over pi times t, where t varies from t equals 0 to t equals pi over 4. And what does that give me? That gives me, well, the r's cancel here, well, one of the r's does at least, so I can get rid of 1r, like so, and that's going to give me minus pi over 4r out front. And inside these square brackets, I'm going to have what? Well, I need to plug in t equals pi over 4. Notice I've got 4 over pi here, so when I multiply that by pi over 4, the 4's and the pi's are both cancel, and I'm just going to be left with e to the minus r squared, minus the lower limit, and that's going to be e to the power some stuff times 0, which is just 1. And if I expand these brackets, well, if I distribute the negative signs, I'm going to get pi over 4r minus let's see, pi e to the minus r squared divided by 4r. Well, I want to take the limit of this thing as r goes to infinity. So clearly, as r goes to infinity, this term, that's going to go to 0 as r goes to infinity. And e to the minus r squared, as r gets very, very large, i.e. goes to infinity, this numerator is going to go to 0, and the denominator is going to go to infinity. So in the top I've got something going to 0, in the denominator I've got something going to infinity, so logically this thing must also go to 0 as r goes to infinity. So this term goes to 0, and this term goes to 0, so this whole thing must also go to 0. So in other words, the contribution of the integral of gamma of f of z dz, that's just going to go to 0 as r goes to infinity. So that takes care of the contribution of the eighth of the circumference of the circle. So in other words, that takes care of this integral because I've just shown that this goes to 0 as r goes to infinity. And now I'm just left with this somewhat trickier integral over L, which is going to be basically over this rotated ray which is facing the origin. So how am I going to do that? Well, let's just set things up. I'm going to have the integral over L of f of z dz, and by the definition of f, that's just e to the I z squared dz. And just like the previous integral over gamma, I'm also going to make a substitution, and the substitution I'm going to make is z equals t e to the I pi over 4. So let's just look at this for a moment and see where this comes from. First of all, if t is a real number, what is the equation of the line z equals t? Well, t is a real number, so that's just going to be a ray along the positive real axis, and I'm going to want to multiply that by e to the I pi over 4 to rotate this ray to this ray. Okay, but I'm starting from this point and I'm going to this point. So I don't want to integrate from t equals 0 to t equals r, but rather I want to integrate from t equals r to t equals 0. Because that's going to take me from the number, well, if I literally write what this point is, it's r e to the I pi over 4. And I want to get from here to here. So the only way I'm going to do that is if I plug in the value t equals r and then t equals 0. Just like that. So that's the reason for the substitution, z equals t e to the I pi over 4. So t is going to vary between 0 and r, but most importantly it's going to start with the lower limit at r, with the upper limit at 0. And when I differentiate z with respect to t, I'm just going to get dz. Well, e to the I pi over 4 is just a constant, so this is going to be, let's see, e to the I pi over 4 dt, which is helpful. And this integral is going to become what? It's going to be equal to the integral from r to 0 of e to the I z squared, and that's going to be e to the power I t squared, e to the I pi over 4 squared, and what's that going to be? Well, I pi over 4 times 2, that's just e to the I pi, that's just I pi over 2. So that's going to give me e to the I pi over 2. And for dz, I'm going to have e to the I pi over 4 dt. So what is e to the I pi over 2 and what is e to the I pi over 4? Well, e to the I pi over 2, first of all, that's just cosine of pi over 2 plus I sine pi over 2, and cos of pi over 2 is just 0. And sine of pi over 2 is just 1. So this is going to give me I. So I'm going to have e to the I t squared times I. So this is going to be equal to I. That was not done very clearly. So this is equal to I. And what about e to the I pi over 4? Well, e to the I pi over 4 in exactly the same way. E to the I pi over 4 is the cosine of pi over 4 plus I times the sine of pi over 4, and cos of pi over 4 is root 2 divided by 2, and sine of pi over 4 is exactly the same value, plus I root 2 over 2. So that helps me somewhat. So this integral here is going to be equal to what? It's going to be equal to the integral. Well, first of all, I'm going to have a factor of e to the I pi over 4. I'm not going to write it in the full root 2 over 2 form yet. So it's going to be the integral from r to 0 of what? E to the it times I, because this term is equal to I. So e to the it squared I squared is minus 1, so that's e to the minus t squared. And is that everything for my integrand? Yes. dt. And what happens to this integral as r goes to infinity? Well, first of all, I want to swap the limits of integration around. So if I swap the limits of integration and multiply everything by minus 1, that preserves the value of the integral. So that's the same as minus e to the I pi over 4 integral from 0 to r of e to the minus t squared dt. And this integral is going to go to, as r goes to infinity, this integral is going to go to minus e to the I pi over 4 times the integral from 0 to infinity of e to the minus t squared. And this integral, as we all know, is the Gaussian integral, taken over the entire real line from minus infinity to infinity. It has value of root pi, but since we're only taking half of the interval, it's just going to be root pi over 2. So this is going to be equal to root pi over 2. And I'll provide a link to how we do this. Basically use polar coordinates, and it's a fairly straightforward process to show this. I'll link you to the Wikipedia article, which basically explains everything you need to know. So this thing is equal to root pi over 2, and that means that I'm going to have minus e to the I pi over 4 times root pi over 2. And if I now plug in my definition, well, not definition, but what e to the I pi over 4 is equal to, it's root 2 over 2 plus I root 2 over 2. And that's going to give me minus root 2 over 2 plus I root 2 over 2 times root pi over 2. And let's see if I can distribute this a little bit. That's going to be equal to negative of root 2 pi divided by 4 minus I root 2 pi over 4. Okay, so that's the last integral taken care of. So I've now taken care of this integral here. I've shown what it evaluates to. So what do I get in total? Well, on the left hand side I'm going to have 0, and what about the integrals in between? So putting it all together, I have what? I've got 0, without the integral on the left was 0 by Cauchy's theorem. What is the first integral? The first integral, if I go way back over here, let's see, I found that it was equal to the integral from 0 to infinity of cosine of x squared plus I times the integral of sine of x squared. So this is equal to the integral from 0 to infinity of cosine of x squared dx plus I sine, well, plus I times the integral from 0 to infinity of sine x squared dx. And I had the integral of the curve gamma was equal to 0 as r went to infinity. And then we're going to have this term here from the contribution over the ray tending towards the origin. So this is going to be minus root 2 pi over 4 minus I times root 2 pi over 4. Okay, now if I just add both of these negative terms to the other side, or to both sides, I'm going to get root 2 pi over 4 plus I root 2 pi over 4 is equal to the integral from 0 to infinity of cosine x squared dx plus I times the integral from 0 to infinity of sine of x squared dx. And we're basically done at this point, because you notice that if I take real parts of both sides and imaginary parts of both sides, I'm going to solve both of these Fresnel integrals. So in other words, therefore, the integral from 0 to infinity, taking real parts of both sides of the equation, that's just equal to root 2 pi over 4. And if I took imaginary parts, I'd get the other integral. So this is also equal to the integral from 0 to infinity of sine of x squared dx, which I think is quite a nice result. Okay, so that's all we've got time for today. If you liked what you saw in this video, please leave a like, comment, and subscribe. And make sure you stay tuned for more videos just like this. Thanks.